In this problem, we want to figure out if our pump can handle scale up. So we want to increase production by 25% in a chemical plant. And we've got a pump that is pumping material between say a tank and a reactor. And we want to know if that existing pump can handle the increase in flow rate. And we want to do this calculation without knowing any details, right? All we want to know is whether or not we can handle a 25% increase. So we don't know any of the other details. We want to do kind of an estimation or back of the envelope calculation. And so one way that we can do this is we can start with basically applying the Bernoulli equation between the pump outlet at position 1 and the reactor inlet, which we'll call at position 2. And so if we take our Bernoulli equation and write it for those terms, this is the pump outlet, so the pump is not part of the system. So position 1 is going to be the pump outlet, so P1 over rho 1g, our velocity head, U1 squared over 2g plus Z1. And then we have frictional losses in the pipe. All right, and so this is going to be with the pipe and in any fittings that we have. And then our P2, the position 2, this is going to be at the reactor inlet. So P2 over rho 2g, U2 squared over 2g plus Z2. We can then take this general Bernoulli equation, we can apply some assumptions. So we aren't told anything about the pump diameter, the pipe diameter, but let's assume that it is constant. Also, we assume incompressible flow. This is a liquid that's flowing, so density is constant. So what that means is that the velocity, the cross-sectional area is constant, the mass flow rate is constant, the linear velocity is constant, and so these velocity terms will cancel out in the Bernoulli equation. Also, let's assume that there's negligible change in the elevation, so we won't worry about the Z1 and the Z2. So if we make those assumptions, this is what we get. And what I've done here is I've taken head loss, our general head loss, and plugged that in here. So we have our fanning friction factor, the equivalent length of the pipe. We'll assume that we'll deal with the pipe length equivalences for any kind of head losses. And then, of course, our P2 over rho g on the left side. So we essentially want to calculate the pressure drop, right? Will our pump be able to handle this? And so we need to see what the pressure drop is going to be for these cases. And so we take our P2 minus P1, and we want to see if, and we set that equal to our head losses. Now what we're going to do is we're going to set our base case as our original scale, right? And our new case is going to be the scaled up production by 25%. And so we're going to take this pressure drop and we're going to assign subscript 1 for the base case and subscript 2 for the new case. And we are going to look at the ratios and see what falls out from the math. So delta P for the case 2 is going to be in the numerator. Delta P for case 1 is going to be in the denominator. And this is what we get. So we're going to apply some more assumptions, right? So we didn't say anything about the piping changing, all right? We want to take all of our existing equipment and piping and see if it can handle this 25% increase in mass flow rate. So the same piping, so the length and the ID do not change, all right? The fluid properties are not going to change, right? But the velocity will change. And where's the velocity? The velocity is in the U squared terms here. Remember also the velocity is going to be in the friction factor. But if we look at the friction factor, remember that we've got the same idea of the pipe, and we bring up that friction factor formula that we've worked with. you'll notice that it is a fairly weak function of the Reynolds number. For laminar flow, it's a strong function, but remember the friction factor, if you look at my cursor, it tends to flatten out as you go when you plot friction factor versus Reynolds number. And so what we can assume then is that the friction factor is going to be about the same for both of these cases. There will be a little bit difference, but it's going to be about the same. So what we can do then is we can start crossing out terms, right? We can start crossing out terms and canceling terms and seeing what this pressure drop ratio is going to be for the case 1 and the case 2. So of course the constants are going to cancel out. Densities, same fluid properties, that's going to cancel out. Friction factors, those are about the same. Length of the pipe is the same, right? The inner diameter, the IDs, are going to be the same, and what we're left with is U2 squared over U1 squared. So our pressure ratio is going to equal U2 squared over U1 squared. And so then what we want to do, we are not scaling up the linear velocity by 25%, we are scaling up the mass flow rate by 25%. And so we need to substitute for linear velocity, we need to express that in terms of the mass flow rate. And so this is what we do. And this is nice and simple because the mass flow rate scales directly with the linear velocity. And so the pressure ratios between our large scale and our small scale case is equal to the mass flow rate for our larger scale squared over the mass flow rate of our small scale, of our base case squared. Our mass flow rate increases by 25%. So that means our mass flow rate of case 2 is 1.25 times our mass flow rate of case 1. And so we can plug that in. 1.25 squared over 1 squared is equal to 1.56. And so what that means is that the pressure is going to increase by 56% if we scale up our mass flow rate. So we scale up by 25%. Our pressure does not scale linearly. It scales with the square of the mass flow rate, and so that will be a 56% increase in the pressure drop. And so what you will need to do is you will need to look at your pump and your pump system curves, and you will need to you can calculate the head, and then you can figure out if that will we then relate remember, because most pump system curves are head versus flow rate, and so you will calculate a flow rate, and then you will calculate the head increase that results from a 56% increase in pressure, and you will see if your pump can handle that. If it can't, then you may need to do something like buy a new pump, or you may look into things like increasing the diameter of your pipes, trying to reduce the head losses due to friction in those pipes.